So for this last little bit here of the section 2.6, we're going to put down two theorems, and then we'll get the final example done. So we have a theorem, and in this theorem we get two important limits. So we have the limit as theta approaches 0 of sine of theta divided by theta. That ends up equaling 1. So this is one important equation. And then the other one is the limit as theta approaches 0 of 1 minus cosine of theta, all that divided by theta, equals 0. So these are two important things that we'll use. There also is a nice little inequality that we're going to write down here. It's kind of its own theorem, which is cosine of theta is less than or equal to sine theta over theta. Is less than or equal to 1 for basically as long as theta is in between negative pi over 2 and positive pi over 2. So this is sort of a interval around 0, and you can get this inequality to hold. If you all read in your textbook, they have a nice, it's on like page 97, they have kind of an explanation as to how you can apply the squeeze theorem to generate some of this stuff. But we're going to just kind of mainly focus on how to use this. So we have our we have kind of everything like this. And we're going to look at example 2, and that's the last of the book examples, and we'll have some other examples of this stuff in practice problems in the section. So we're going to look at what is the limit as h approaches 0 of sine of 4h, all that divided by h itself. So this looks like its limit as h approaches 0, sine of 4h over h. It looks very close to what we have here. The problem is, instead of sine of theta over theta, we have a 4h up here. So the top part doesn't match the bottom part. So what we're going to do is basically we got to get a 4h down here. So we're going to say, all right, first of all, limit as h approaches 0. I'll write this one out we'll write it out this way. We have we're going to need extra 4's in here. So I'm going to put a 4 over 4 out front. 4 divided by 4 is 1. So if I multiply what I currently have by 1, that doesn't do anything. That leaves leaves the value the same. Like sine of 4h over h times 1 is still sine of 4h over h. What I can do then is I can bring the 4, pair the 4 up with the h down here. And this is a constant, and we're able to push constants out front of the limit by those basic limit laws back in, what was that, section 2.3. So we got this top 4 is on out. We have limit as h approaches 0, sine of 4h divided by the same 4h. So to finish up so I can apply the theorem, now that I have sine of the same thing that's inside the parentheses as is downstairs, I can replace the symbol theta. So we're going to let theta equal 4h. And we'll rewrite this that way. So if you think about it, if 4h is approaching 0 and if h approaches 0, then 4 times something approaches 0 still approaches 0. So theta approaches 0. So we're able to get that if h is approaching 0, theta still approaches 0, because something approaching 0 multiplying it by 4 still approaches 0. Sine of 4h over 4h, this becomes sine of 4h we're replacing with theta over 4h we're replacing with theta. And then by our theorem, that little equation we have up here, limit as theta approaches 0 of sine of theta over theta equals 1. So limit as theta approaches 0, sine of theta over theta equals 1. And then the overall limit here is going to be 4. So the limit, if we look at, say, what's the original problem, the limit of this is equal to 4, and the work we have to verify that is all down here. We had to rearrange stuff where we got the same thing in the parentheses of sine as was downstairs, and once we had that, and we had that isolated, we could change the variable name using the substitution over here, and then we were able to apply the theorem on this part and realize that all actually, by the theorem, that all is 1, and then 4 times 1 is 4.